Hello everyone, my name is Gustavo Lahr. I'd like to present a hybrid model-based evolutionary optimization with passive boundaries for physical human-robot interaction. So during a task like wrist rehabilitation, for example, which is the case example here in this task, what we want to do is the robot to improve its performance for each user. So different person interacting with the robot means different behavior. So in order to do that, we choose to use evolutionary optimization because it doesn't depend on gradients, so we don't have to know a model of the objective function. But the problem with that is that the algorithm may choose any controller on the search space, and that may lead to unstable situations or very high oscillations. So we want to guarantee stability for any controller tested during the optimization. In order to do so, we add in this evolutionary, we add model-based passive boundaries to guarantee stability. So what we do, we try to avoid unstable cases by modeling the Z width of the controller of our system and guarantee that we are optimizing only on that region. So we use the admittance controller and we model the impedance on the interaction port. The interaction port is the one highlighted for the torque exchange between the user and the velocity developed by the robot. So we chose to minimize the torque and the time, because minimizing the torque means a smoother experience, and minimizing the time of the whole task means that the robot is trying to have a more dynamic behavior. So in this sense, we're optimizing a trade-off, which is the case for multi-optimization techniques. And this one also, we are adding the last constraint is the constraint to guarantee that we are optimizing only in the Z width region. With this, we're actually guaranteeing a faster convergence because right now our search space is actually constrained, and improving the shared autonomy because right now the robot can change the controller freely without harming the user. To check that, what we did was we measured the unconstrained and compared with the constrained optimization. If you see the constrained results, we can see on the left the admittance parameters, stiffness in the bottom and damping on the top. And in the right, we can see how the metrics also developed through the generations. We see an average, so this is 10 generations, 5 users, 5 trials for each generation, and for 3 subjects. So we can see that for each subject, the controller is actually capable to change its behavior, to change different values of controllers and achieving different values of the metrics. We can see the same plot for the constrained case, and we can see that we have a smaller uncertainty region because now our search space is constrained, but also you can see differences because the controller is trying to adapt for each person. If you take a look on the numbers, we can see that for the average here on the unconstrained case, we achieved optimized values. For the constrained case, we are also optimized. However, the difference between the unconstrained and unconstrained, it's the unconstrained achieved better results. That's because it can sample any controller it wants. However, for some cases, we actually achieved a more unstable cases in the unconstrained situation. So if you want to discuss more, I'm free and I'm open. Feel free to email us. Thank you very much.